It's good to be here. Appreciate getting the invitation. This is quite a small room. We've got, I don't know, probably 80, 90 folks here, which is a really good crowd, and it still feels like it's half empty. So if you can't hear me in the back, you can raise your hand, and I'm not going to do anything different because it was your choice to sit in the back. You could move up, but I just appreciate your waving your hand up there. That way I know you're awake at least. I've been at Oak Ridge National Lab for about 6 years now. I started working in fusion. Actually, my doctorate was working in design optimization of a active passive damping structure. So fusion was not an area that I studied, either undergraduate or graduate school. But I started at ORNL 6 years ago. And as Dr. Margrave said, it could change the world. Or it could always be, as it is today, the energy of the future. The old joke, fusion's the energy of the future and always will be. For the standpoint of an engineer, fusion is a wonderful place to work, and that's how it could change your life in the near future, in that Oak Ridge National Lab, just up the road, is expanding its fusion footprint. It's not only is there a division within the lab that works in fusion energy where I work, but the US ITER project office, which I'll describe in a minute, also is based in Oak Ridge. So for engineers looking for jobs, it could change your life in the nearer future. So what I am going to talk about is the past, present, and future of fusion, where we've come from, where we are today, where we will be, by answering these questions. For those of you who are not familiar, I'll do some kind of basic, here's what fusion is, what's the motivation for doing research in fusion, where are we today with it, and then that leads to the next question, what is ITER, which is the largest scientific experiment ever done in the history of man, if by large you mean expensive. And then what's next? What's after ITER? I should say I'm not going to talk about cold fusion, and if any of you have questions about cold fusion, I will not answer them because I know nothing except that it doesn't really work. There are more exotic technologies, and in fact there's industries like Lockheed Martin, Skunk Works that are developing, it's not so exotic, but are developing alternative fusion ideas than the ones that I'm going to present here. Though one of those ideas may end up working, and in 30 years we may be driving cars with rotary Wankel engines, but there's one technology that's been largely worked on over the last number of years, and it may not be the best one, but it's the one we know the most about, so that's what I'm going to discuss. Quick disclaimer, do we have any non-engineers here? There's two types of people in the world, right? Engineers and then not engineers. Okay. Physicists, any physicists? Okay. Which is wonderful. I work with a lot of physicists, and some of them are actually really nice people. But I'm a mechanical engineer, and although I am doing more kind of project leading now, so maybe I'm an engineer, but in any case, I am not a physicist, and so for those of you who are physicists and have the physics questions, I'm not going to do a whole lot to answer those, and I can refer you to some outstanding people who can answer all of your questions. I've learned enough physics to impress engineers. Okay, in the news, and this is just in this last month, Science Magazine has an article titled Twisted Logic, which is on a fusion experiment that's being built, is about to begin operation in Greifswald, East Germany. It's one of the projects that I've worked on. We've collaborated with the Germans in developing some portions of this experiment called the Stellarator. And Time Magazine, I don't know if you can see in the upper right corner, this is November 2nd, 2015, so run to your newsstand today, article on fusion. It's something that is even outside of just the arcane technical literature, but even in the popular literature, it's big stuff, and always will be. So what is fusion? Essentially, fusion is the joining of these subatomic nucleons, the nucleus with the electrons stripped from them, of light elements to join heavier elements. The lighter elements join together because of the strong nuclear force. You ever wonder, especially those of us who are engineers, when you're taking your chemistry, material science class, the only classes where we really look at subatomic levels, why it is that in a helium atom, upper right corner there, you've got two protons, and we know electrostatically those two protons should be repelling. Why don't they? Why do they stay in a nucleus together when there is no counter negative charge to try and keep them together? Well, it's because of this strong nuclear force. And so if you can ever get two nucleons, two subatomic particles, and charge does not matter, whether it's a neutron, whether it's a proton, if you can get them close enough together, this strong nuclear force takes hold. The problem is you've got to get them within about a femtometer, 10 to the minus 15th. And that's really hard to do, especially when you have negative or positive electrical charges that are repelling. So they don't want to get together. And unlike the electrostatic charges where it's relative to their position, so the closer they get together, the stronger that force gets. The strong nuclear force is nothing, 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 nothing. Then you get within a femtometer and then it takes hold. So the question is, how can you get two particles that close together? And I should say, well, I'll get to how the energy is produced in a second. So all nuclear reactors that actually do something, that actually produce energy, are fissile reactors. They're fission reactors using uranium, plutonium. There's ideas to use thorium or other elements. You take the big clumpy atom and you split it, and energy is released. The idea of fusion is you take the very small atoms and put them together. And anytime you're going to a higher energy state, this is average binding energy per nucleon versus number of nucleons. And the further you go up this chart, the more stable you are. So the most stable elements are iron or some isotopes of nickel. Those don't want to be anything else. But you take a big heavy atom like uranium and you split it, and energy is released and it becomes two more stable atoms. Contrawise, if you start with helium or isotopes of hydrogen and stick them together, they join to become something heavier. And when they join, they end up being a little bit lighter than the resulting product is a little bit lighter than the two elements were to begin with. The amount of energy released is E equals mc squared. The reduction in mass of the new element is converted into energy. So D and T, deuterium and tritium, which are two isotopes of hydrogen. So deuterium has proton, 1 neutron. Tritium has proton, 2 neutrons. You put them together, you get helium plus another neutron. And this is kind of the favored fusion reaction. If we ever produce energy with fusion, this is probably how it's going to be done. And the mass before, you can see here, I'm not going to go over everything on this slide, but the mass before is about 5.03 atomic mass units. The mass after is about 5.01. Where does that mass go? It goes into energy. How much energy? E equals mc squared, about 2.8 times 10 to the minus 12 joules. So, fusion is 99% of the energy in the universe, because it's how all the energy from stars is produced. Some interesting figures. The surface temperature of the sun is about 6,000 degrees. The temperature at the core is about 15 million degrees. That sounds impressive. I'll come back to that, though. The deuterium-tritium reaction occurs about 10 times that temperature. If we're ever going to produce fusion. The sun loses about 4.2 million metric tons of mass per second. Oh dear, our sun is losing a lot of mass. At that rate, it'll be gone in about 16 trillion years. Sun experiences gravitational fusion. Why does fusion happen in our sun? Because it's so massive that the gravity pulls these ions together within a femtometer of each other. So if we want to produce fusion on Earth, all we need to do is get the mass of the sun and put it on Earth, and voila. Well, that's not an option, right? So that is gravitational confinement. Okay. So again, we got to get these two nucleons within a femtometer of each other, and we've got to overcome the electrostatic resistance to that. It happens in the sun and in all stars because of gravity. There's two ways that we are trying to produce this on Earth. One is with inertial confinement, and National Ignition Facility in Lawrence Livermore National Lab in California. Any of you see Star Trek Into Darkness? A few. The engineering room was the National Ignition Facility. I guess they figured a place that had a lot of interesting ports and tubes and electronics coming out. Looked like an engineering room for Starship Enterprise. What they do there is produce some very high-powered lasers that all converge at one point. They've got 24 lasers there, which each are order of magnitude more powerful than the most powerful laser in the world. They all converge at one point, and as a result, they essentially implode a deuterium-tritium pellet in order to produce fusion. What I work on and what we work on at Oak Ridge National Lab, and really the primary international efforts, are in magnetic confinement fusion, where your plasma is confined through a large magnetic field. So how this works is large magnetic field is created in order to confine a plasma. What is a plasma? Plasma is really just a gas where the particles are so energetic that the electrons dissociate from the nucleus. So you have a bath of electrons and neutrons. And the great thing about that is they have a charge. And when something has a charge, it can be controlled in a magnetic field. You have a neutral particle and it's not affected by a magnetic field. So plasma, the fourth state of matter, and you see it every day: static electricity, lightning, aurora borealis, fluorescent light bulbs. At the lower left-hand corner is an industrial plasma used for etching. It's harder than it looks. This may be a little dated, this slide. Spider-Man 2, and you see Spider-Man 2. The flaws in Spider-Man 2 are legion. We can talk about that at some point. It was silly to the point of being laughable, but anyway. I guess if you're going to say a person can be bit by a radioactive spider and climb walls, then maybe that's, but you want to get the science right. You want to get the science. All right. Magnetic confinement reactors generally rotate the plasma in a donut shape, in a toroidal shape. There are several concepts for doing this. The most common is called a tokamak, which tokamak is a Russian abbreviation. The Russian term for toroidal chamber with magnetic coils. You take the first two Russian letters from each of that and it becomes tokamak. In order to overcome the electrostatic forces, the plasma must be heated to, with a deuterium-tritium plasma, 150 million Kelvin. So the problem really comes heating the plasma, and this is done. Again, 150 million Kelvin is 10 times hotter than the core of the sun. If we wanted to create a fusion with a deuterium plasma, it would have to be 1 billion Kelvin, which is a little bit harder to do. It's about 70, 80 times hotter than the core of the sun. So currently, the largest tokamak is in Culham, England, the joint European torus, and here we see a plasma being magnetically driven. You can kind of see where it's interacting with the walls is where you see those glows. And generally, these plasmas are, that was probably a deuterium plasma. Before I get into, come back to how these tokamaks work and where we're going next, how far are we is the question everyone has. When will we actually have fusion energy? Let me talk a minute for why we should be developing fusion energy. And this is kind of the takeaway, as Dr. Margrave said, if fusion works, if we can get it to work, then all of our energy supply problems are done forever. There still is a distribution issue, and that's, our energy problems have production and distribution issues. So But we'll never ask again, where's the energy going to come from? Because we have enough deuterium in our ocean water to last our current energy needs for about 2 billion years. And I presume by that point we'll have thought of something better. Some of the negatives of our current energy sources. Now this is coal-fired. I know that currently coal has become the second largest energy producer in the United States. The first is now, anyone know? Natural gas, yeah. Which is a little cleaner than coal, actually quite a bit cleaner than coal. Interestingly, the US now in its greenhouse gas production is back to where we were in the 90s. The Europeans who have decided to go the route of renewable sources more than natural gas have not been able to achieve that. So anyway, little side point. So coal-fired plant, that's a gigawatt, 1,000 megawatts, enough to power about 500,000 homes, consumes 9,000 tons of coal, and coal still produces roughly 35% of our electricity. Produces 30,000 tons of CO2, 600 tons of SO2, 80 tons of NO2, while a similar fusion power plant would require about a pound of deuterium, 3 pounds of lithium-6, and it doesn't use lithium-6 to produce energy, but the lithium-6 is needed to produce the tritium. Deuterium is a stable isotope of hydrogen that exists naturally. Tritium is not stable and has a half-life of about 12 years, so it does not occur naturally. So if we were to do a deuterium-tritium reaction, we'd have to produce tritium. But anyway, that can be done with lithium-6. That would produce about 2 pounds of helium-4, half pound of neutrons, and 1,000 megawatts of energy. So it's pretty impressive how much energy you get with a very little amount of raw material. So energy uses of various populations so on average, the average person in the world uses 2.43 kilowatts. You can imagine every person, the 7 billion people in the world have about 25 100-watt light bulbs. Oh, that's incandescent light bulbs. We maybe need to transfer this to compact fluorescent terms. But anyway, imagine we still had 100-watt incandescent light bulbs. Walk around with 25 incandescent light bulbs over their head. In the US, it's more like about 100. We're about 4 times the world average. Now, of course, that's not residential consumer use. That includes all the power that's used for running plants and all of our different need for energy consumption. European nations are a little lower than the US by about half. China is about 1/6. India, more like 1/16. So in 2006, that produces, that requires 16 terawatts to power the world. Now that's, if we look just from population growth, and perhaps a little more, on the order of 10% more energy usage worldwide as non-industrial nations industrialize, in just 15 years, that could be up to 23 terawatts. If we industrialize more quickly, then that could be 3 times the current energy. And given that over a third of the world's population is in this 1.5 to 0.6, and those are both nations that are industrializing at a great pace, it's not too inconceivable that we might be closer to that bottom number than the middle number. So again, where is that energy going to come from? What the Chinese have been doing is building coal plants every few weeks as they industrialize. That's the easiest solution. They're also building nuclear power plants about one every 6 weeks. So the pros and cons of these various energy sources. And so just very generically, now understanding fossil fuels, again, coal, natural gas, there are distinctions there. And the good thing about them is they're easy to extract. There is a limited supply. and we'll talk about that a little more in a minute. Pollutants and whatever you're feeling about global warming, they are greenhouse gases, they are pollutants, and there is nothing good that happens from dumping lots of carbon oxides, sulfur oxides, and nitrous oxides into the atmosphere. Renewables all look great except this energy density issue, and I guess we could have put cost of energy. Germany now produces 20% of its power from renewables, and electricity costs twice in Germany what it does in the US. And that's just to get to 20%. And that, some people feel, may be close to a ceiling, at least with current technology. Fission energy, which in the medium term may be really the only solution as China and India industrialize. Difficult to extract raw materials. The long-term toxic waste is a problem. The nuclear proliferation risk is a problem. When I joined ORNL in 2009, there was talk of the nuclear renaissance. And in fact, I'm a part of a directorate in Oak Ridge National Lab, Nuclear Science and Engineering. It was the first time that Oak Ridge had a directorate that had the name nuclear in it in about 30 years. About 30 years ago, 3 Mile Island was one disaster. And then just as we were getting ready for the nuclear renaissance, what happened? Fukushima. And Fukushima, from a human standpoint, there was very little real effect. But from a public relations standpoint, it was a disaster. And a lot of the European nations, France being a notable exception, really backed off nuclear, and the US backed off somewhat. So fusion has none of these drawbacks. Raw materials, deuterium, which is available in the ocean water. Pollutants, pretty much none. I mean, helium. I guess if you want to talk in a real high voice, fusion's a great idea. The amount of helium is quite small. No long-term toxic waste, no proliferation risk, almost no safety hazards, and a very high energy density. If we look at, and this is from 2006, with the fracking boom, these numbers have changed somewhat, but coal, we've still got lots of coal, and if we were to, looking at the second and third column, the second column says, if we were to go just with this energy supply, with our current energy needs, 16 terawatts around the world, how long would the known natural resource last? So if we wanted to power the world with coal, we've got enough coal to power the world for 200 years. But then you're burning coal for 200 years. If we just use the current coal usage, we'd have enough to last for 900 years. So lots of coal. It's why, again, China is building coal plants willy-nilly, and why there's a pollution problem in just about every major Chinese city. Oil, if we were just to power the world with oil, we'd have enough for 20 years. Natural gas, as I said, with fracking, those numbers would go up. With standard uranium fission reactors, it's 20, but if we look at the next generation of the generation 4 fusion reactors, that's expanded. And again, fusion, deuterium, 2 times 10 to the 9th, 2 billion years. And I guess if we start with deuterium-tritium, we've got enough for 20,000 years. And I think within the next 20,000 years, we'd learn how to make the deuterium-deuterium reaction work. So thinking long-term, and again, we're fine today. And the US is around energy independence, saying we, our nation. But really the world has enough supply to meet energy needs for today and for the next 10 years, probably the next 20 years. But thinking in the next 50 years, non-renewables are non-renewable, okay, plus pollutants, greenhouse gases, et cetera. Widespread use of fission, we've got nuclear proliferation issues, long-term hazardous waste, and even uranium supply. If we were to start ramping up, France provides about 90% of its electricity through nuclear power plants. If the whole world were to do that, we would have a uranium supply issue. So, said fusion is abundant. The deuterium in half a bathtub of water plus the lithium in one laptop battery. This is another way to look at it. And deuterium is a stable isotope that naturally occurs in ocean water. About 1 in every 6,700 atoms of water in the ocean is not H2O, it's HDO, hydrogen, deuterium, and oxygen. So, and it's very easy to extract. Tritium, however, is a radioactive isotope with a half-life of 12 years. And currently, worldwide tritium supplies for non-military use. It's also used for thermonuclear weapons. But it's a very limited supply, generally produced by fission reactors, and it's very heavily controlled. However, the deuterium-tritium reaction also produces this high-energy neutron. If that high-energy neutron hits lithium-6, it produces tritium. So the idea is, if we get this deuterium-tritium reaction to work and put lithium-6 in the way of it, we should be able to have a self-sufficient supply of tritium to continue. Okay, so that's why we need fusion. And here, again, I'm thinking in a time horizon of around 50 years. So, fission energy. How did we get fission? The first uncontrolled fission reaction was in Los Alamos, July 16, 1945. And then, of course, not long after that, was the bomb that was dropped on Hiroshima. And just 11 years later, the first controlled fission power. Wasn't a lot of power, 50 megawatts. Again, your average power plant somewhere on the order, 500 to 1,000 megawatts. So the purpose of this power plant was not to produce cheap electricity. It was to demonstrate that you could produce electricity with fission power. So 11 years from that first uncontrolled reaction to producing electricity. And then the first in the US was a year later in Shippingport, Pennsylvania. The first uncontrolled fusion reaction was in 1952. So 11 years later, we have fusion power, right? Well, 63 years later, we still have yet to have our first commercial fusion power plant. The Ivy Mike was the first fusion explosion, 10.4 megaton bomb. It's about 450 times the energy of the bomb that was dropped on Nagasaki. So where are we today? So fusion people can be so pessimistic. Well, you get two types. You get sometimes the folks on television who talk about how wonderful it is and how it's just around the corner. Most people don't believe that anymore. We could talk like that in the 60s and maybe into the 70s, but after saying fusion is just 10, 20 years away, eventually people don't believe you anymore, and many of us have gotten realistic. Now, for engineers, fusion is great because engineers are trained as problem solvers, right? We love solving problems. In fusion, the problems are everywhere. There is no end of interesting problems to try and solve. So fusion's a great place to work. But in terms of becoming a power source, there are some obstacles, and I hope in the next 15 minutes to impress on you how difficult this is and how cool it is. Okay, so are there any fusion experiments operating today? The answer are, and we've got a bunch of plasma physics experiments shown here in any major industrialized nation. And I could go over the long list. The Department of Energy in the United States right now supports 3 plasma physics experiments. One is in Princeton Plasma Physics Lab in Princeton, New Jersey, National Spherical Torus Experiment, NSTX. One is run by General Atomics in San Diego, La Jolla, California, and one is run by Massachusetts Institute of Technology. But the newest and coolest ones are in Asia, the K-Star Tokamak, and in Hefei, China, the East Tokamak, and really both of these designs are US designs. These are the first fully superconducting magnets. So both of these are made with supercooled superconducting magnets that operate at 4 Kelvin. So, has energy produced from fusion power ever been put into an electric grid? Okay, next question. Do experimental reactors perform deuterium-tritium fusion reactions? And a little longer answer, most do not. It's not because they can't, but it's because handling tritium is difficult. And to handle more than a few grams of tritium requires all kinds of licensing. It's expensive, it's difficult, you have to be very careful. Plus, deuterium-tritium reaction produces these high-energy neutrons, which does make everything that it hits radioactive. So it's just a lot more expensive if you're going to produce these deuterium-tritium reactions. So instead, we generally do deuterium, hydrogen, helium plasmas, just so we don't have to mess with this. Like in the D3D Tokamak that's run by General Atomics in California. They can run a plasma, open up the machine, and go in there after maybe a few hours. You get a few neutrons even with just a deuterium plasma, but it's okay for humans to go in after a few hours. ITER, which I'll talk about in a minute, when it runs its deuterium-tritium plasma, no human will be able to enter the reactor area until it's decommissioned. So it's a challenge to run a deuterium-tritium plasma. Has it ever been done? And the answer is yes. Okay, finally I can say yes to something. The first deuterium-tritium plasma was done in Princeton Plasma Physics Lab in 1997, produced 10.7 megawatts of thermal energy and achieved temperatures of 500 million degrees. The Joint European Torus, which is the plasma that I showed you earlier, produced 16 megawatts of energy with a DT plasma, and they're planning on running a DT plasma again in a couple years. As is, I didn't put it here, but there's a experiment they're building in Japan, JT60SA, that also will run a DT plasma sometime in the next 3 to 4 years. ITER, I keep using that word. It's scheduled to run a DT plasma in about 2030. Has any reactor ever produced more energy than it has consumed? And the answer is, well, that depends what you mean. Not when it's running DT. But again, a lot of these reactors run deuterium plasmas, and the JT60 reactor in Japan got a Q. Q is energy out divided by energy in. So if that's less than 1, it's taking more energy to run than you would get out. JT60 created a plasma that, if it had been a deuterium-tritium plasma, would have had a Q of greater than 1. ITER is expected to achieve a Q of 10 during its deuterium-tritium operation phase. So I've given a lot of bad news, and it may sound like we've just been working at this forever, pouring money into a big hole. But we have been making progress. We've been getting confinement times density is kind of a figure of merit for how effective the fusion reaction is. And if we look at that versus ion temperature, to get what's called ignition, that is a self-sustaining reaction, a reaction that's producing neutrons that you no longer have to be pouring energy into in order for the reaction to continue. As each decade goes by, we're getting closer. And when ITER begins its deuterium-tritium operation, we will be there. ITER is Latin for the way. Actually, the idea, it's the Latin word that means the way. The idea for ITER came from a meeting between Reagan and Gorbachev in 1985, when they said this thermonuclear reaction, let's do something positive with it. Let's do fusion energy research. And at that time, they said, let's call this the International Thermonuclear Experimental Reactor, ITER. Since then, if you go to the ITER website, iter.org, ITER.org, you won't see those words anywhere, because it was kind of believed that using the words thermonuclear and experiment and reactor in the same term was not good press. So now they say it's ITER, Latin for the way to new energy. Anyway, construction has begun and is well underway. You can see the lower right-hand corner, that little stick, that's a person in relative size. The ITER superconducting magnets, which It's this D-shaped magnet here. There will be 18 of them. They'll each be 360 tons, the weight of a fully loaded 747, and they'll operate at 4 Kelvin. And just to give an idea, deep space, if you go to the farthest reaches of space, farthest away from the farthest star, you're at about 2 to 3 Kelvin. The background radiation of space is 2 to 3 Kelvin. It's very hard to get to 4 Kelvin. The deuterium-tritium reaction, again, that'll happen just a few feet away, will be at 150 million Kelvin, 10 times hotter than the core of the sun. So I think you'll probably have the highest thermal gradient of anywhere in the universe going on in ITER when it's operating. It's about 200 feet high, 223,000 tons, or about 50 million pounds, and will generate 500 megawatts of thermal energy with 50 megawatts to operate. So that all sounds pretty cool. And it's a partnership between 7 national entities: the EU, the US, China, Russia, Japan, Korea, India. So over half the world's population is represented by these different national entities. It's being built in Europe, and Europe has the largest piece of this pie, and Japan has the second largest. But each of the partners are contributing. And then, as I said, the United States office for ITER is managed by Oak Ridge National Lab. It's just down the road from me. And I probably spent about a quarter of my time working on ITER relevant work. So being built in the southern part of France, not far from Marseille, in a city called Cadarache, or near a city called Cadarache. And here's kind of a view of what the site will look like. The Tokamak Hall in one spot, a completely separate building that'll have all the power supplies, office buildings. And here's a picture from September. So it's not just a big hole in the ground. What you see here is the assembly hall. They just put a roof on it, which was, I don't remember how many tons that roof is. It's maybe 10 tons, real heavy. You can't see so clearly here, but there's a little circular area here, which is where the Tokamak will be. This is an older picture, but this is the vibration isolation pads that they're putting down where the Tokamak will be placed. All right. I'll leave going over the technologies of ITER for any Q&A. Okay, a lot of assembly required, but hey, took 100 years to construct Notre-Dame. ITER will be less than that. So what's after ITER? Presuming that the schedule for ITER has just been rebaselined, and the plan is to begin operating ITER about 2026, I think, is the latest starting schedule, and to do deuterium tritium sometime in the 2030s, to have that Q equal 10. What's after? Well, after, the plan is to develop a demonstration fusion power plant that will actually put electricity on the grid. And for fusion to be cost effective, you need a Q of about 25. Because you not only have to produce more energy than is being put in, but you've got to account for downtime, you've got to account for all the other infrastructure that's being used to generate the electricity. This is a slide that I stole from the European Roadmap. So the Europeans, the EU, is very serious about developing a path to demo. I know you can't see all this, so if I enlarge a few of those lines, okay, the top line talks about developing plasma operation and shows ITER, and it's got ITER Q equal 10, ITER steady state. If you look on the bottom line, it says demo, and at the very bottom we have the timeline. So 2010, 2020, 2030, 2040, 2050, and you see fusion electricity is before 2050 is the current European plan. Now I would say this schedule is very optimistic. Seeing watts in the grid, if we see watts in the grid for fusion power, it will probably be because the Chinese have decided to do it. They're putting a lot of effort into fusion as well. Yeah, that's 35 years, and if you've been around fusion for a little while, 35 years is just a drop in the bucket. I was at the The largest fusion technology conference takes place in Europe every 2 years. It's called the Symposium on Fusion Technology. And 3 years ago, 2012, it was in Liège, Belgium, and they had the BBC science editor interviewing a set of fusioneers at one table and a set of power industry people at another table, all from Europe. Power industry people who knew enough about fusion to talk intelligently. And of course, the question came up, when will we have fusion energy? When are we actually going to put power in the grid? And one of the power industry people said, and I think this is a very good answer, we will have it when we need it. Do we need fusion today? We don't. We really don't. Will we need it in 2050, 2060? It's hard to predict what the world will be like in 30 to 40 years. It's quite likely that we will need it sometime this century. And so it's worth spending the time to be ready. Another interesting answer I've heard to that question was from some scientists at MIT that were interviewed and asked, when will we have fusion energy? And one of them answered, and I thought this was also a pretty clever answer, we'll have fusion energy in $80 billion. I don't know if that number is exact, and that sounds like a pretty big number, doesn't it? Till you say, okay, the US spends about $2 billion a year on ice cream. Vladimir Putin spent $50 billion to run the Sochi Olympics. $80 billion is a lot of money. And we don't know if it would be exactly $80 billion. And if someone here wanted to write a check for $80 billion, it's not like we would have fusion power tomorrow. I think we could in the next 20 years. So presuming that that number's right, $80 billion, the US fusion budget currently is about $400 million a year. So $400 million a year, how long does it take you to get to 80 billion? About 200. So anyway, I'll just leave that as it is. So the past 50 years, as we have been moving towards better, more advanced fusion results, it's primarily been driven by plasma physicists. I'm a mechanical engineer. What's my skin in the game? Well, ITER is the first really large-scale project where it's been appreciated. You need to not only know about plasma physics, but there's a lot of advanced engineering and technology that's required to make this work. The thermal management, the design against fatigue and creep, material survivability in an extreme environment, and I can go into what's meant by extreme environment, but plasmas, neutrons, helium, hydrogen, extremely high heat fluxes. Some of the plasma-facing components in a fusion reactor will experience kind of space shuttle tile levels of heat flux. Heat fluxes that are not far from what you'd experience if you were on the surface of the sun. The problem is, space shuttle tile experiences one hit and then you take them off and replace them. In a fusion reactor, it's got to operate for 10 years. So imagine a space shuttle that's falling for 10 years. Okay, how are you going to make those tiles work? And in order to test the materials that we need to develop, we need the fusion reaction, and it's very hard to produce. Anyway, last slide. This is kind of the problem. Nobel laureate in physics Pierre-Gilles Lejeune said, we say we will put the sun in a box. The idea is pretty. The problem is we don't know how to make the box. And of course, making the box is an engineering and technology problem as much as it is a plasma physics problem. So, any questions? Yes?
What's the current thought process or scheme of how to manage the energy and extract it from inside the machine? And two, what are you going to do to manage those 14 MeV neutrons?
Okay, so first question was, how do you extract the heat? And then the second question was,
what are you going to do to manage 14 MeVs because your magnetic confinement won't be right?
Yes, so how do you manage the 14 MeVs and how do you extract the energy? Energy will be extracted from, oops, I'm going the wrong way here into my backup slides, from two regions, largely from blankets where there will be flowing, well, one concept is, and this concept is very clever in that you both do energy extraction as well as tritium breeding. A blanket that's got a flowing lead-lithium eutectic will both pull heat out of the reactor region into a place where you can boil water to turn the turbine, as well as lead-lithium will have lithium, and that's where the 14 MeV neutron turns lithium into tritium. Then you extract the tritium from that lead-lithium eutectic. The 14 MeV neutrons, as you can see with ITER, there is, well, maybe it's not completely visible here. ITER has shielding for, say, the cryogenic magnets. So you can't have too many 14 MeV neutrons hitting your 4 Kelvin helium, liquid helium magnet region. So there's shielding to stop the neutrons. There's, of course, the lead-lithium eutectic will be stopping the neutrons. There's concrete. But ITER and any fusion power plant will have a bioshield inside of which a human can't go. So everything done inside the vessel will have to be handled remotely because things just become too radioactive.
So you're circulating, in that concept, the circulating lead eutectic won't affect your magnetic field shape?
It won't affect the magnetic field. It will be difficult to flow lead-lithium when you have in ITER, the magnetic fields will be about 6 Tesla. So that is a current area of research, we'll say. And these are things, again, we don't have anything in the world that can produce any volume of 14 MeV neutrons, so it's difficult to test. Really, I think the bigger problem, I think the problems of flowing lead-lithium in a magnetic field are not insoluble. A problem that could be unsolvable is what material can have a continuous 14 MeV neutron flux along with this high heat flux and survive for any length of time. That really is one of the biggest challenges. They measure radiation damage in what they call DPA, displacement per atom. That is a first wall, the plasma-facing wall, if every atom in the lattice gets moved one time, then that's 1 DPA. And in a fusion power plant that operates, with a duty cycle of about 80%, you'll get about, I'm trying to remember the exact numbers, between 2 and 5 DPA a year. So if you want something to last 10 years, it's going to experience 100 DPA. That is, every atom in the lattice is going to be displaced 100 times. What happens to that material? It's a mess. You also get transmutation. If tungsten is your plasma-facing material, tungsten will transmute into rhenium and osmium if it's going to be there for 10 or 20 years. These are, I'm just, again, engineers, love problems, lots of problems. Okay, good questions. Did I answer both your questions?
I still don't fully understand how you would get a sizable recovery of the heat out, but that's okay.
Well, yes, you'll have these blankets pretty much throughout the reactor, and you'll have either flowing lead-lithium or there's thoughts of molten salt.
Thank you.
You're welcome. Any other questions?
In regards to, I guess, them building it, since it's technically stable inside, let's say if somebody were to make to, I guess, let's say, safety-wise, terrorist-wise, if they were to attack it, can you control that? Would it be just, like I said, they drop a fusion on top of, fission on top of fusion, would it blow half whole country, or?
So the question is, what are the safety issues? So if you either had an instability in just the operation of the reactor, or if you had a terrorist attack, what would happen? And the answer is not much. The reaction is so hard to develop, to make it happen, that if, say, a superconducting magnet blew and the reaction became unstable, it would take a couple seconds to burn out, and then that would be it. What if someone broke the vacuum vessel and lost confinement? Not a great thing. You'd have a couple grams of tritium that would go into the air. What are the consequences of that? Well, if the tritium got into the water supply, a couple of grams of tritium, it's not a great thing. It's probably a little worse than if you were to, eat 10 bananas at once. It's nothing like what it would be expensive to deal with. That's because, again, any repairs would have to be done with remote handling. You couldn't have a human being go in there because the neutron flux is going to be too high for humans to operate in that environment for some time. But if you're a few miles from any habitable city, there really would be no consequences. There's just not enough material to produce high levels of radiation that will extend beyond a very close boundary. I mean, it's really hard to get a thermonuclear reaction working. The thermonuclear weapons, to get a hydrogen bomb to work, you have to have an atomic bomb start the reaction. You got to have a uranium bomb in order to get the deuterium tritium bomb to work. Yes?
So you said before that they think they can produce the new system that'll get a better Q rating of 10 or something. Do you know what exactly they would have improved on that actually produces Q of 10 instead of the Q?
What do we have to improve to get that Q up? And part of that question would have to be answered by a plasma physicist, because it has to do with confinement times, confinement levels, plasma pressures. Let me back up one step to say, why are we doing ITER if ITER is not going to put watts in the grid? What ITER will do is it will demonstrate the feasibility of the plasma physics required for a fusion power plant. So once we have ITER Q equal 10, we will know that we can produce the proper physics conditions for a fusion power plant. But ITER will have a duty cycle of about 3%. So what we won't have is, can we develop the technology that can produce a fusion power plant? As I said, materials that can handle these extreme environments. So I'll just maybe give in my non-physicsy background, I think to get the higher Q levels, I think they would need either a scaled up, larger reactor in order to produce the kind of plasma physics conditions, or much higher magnetic fields, which there are some technologies, high temperature superconductors, which can operate at liquid nitrogen rather than liquid helium temperatures, so it's much easier to use. Can also produce much higher fields. The technology is not ready for prime time yet, but that's something, again, when we think 50 years from now, there's a lot of technologies that might be available that are not available currently. So that's a short answer, and I could get you in touch with some plasma physicists if you want the answer from that side of the equation. But I'd say we also need the technologies to solve these other issues, the removing the heat, being able to handle the environment with the neutrons, the helium, the high heat fluxes. Yes?
We have some devices around the world that are able to accelerate particles to very high speeds, and consideration being to have some kind of beam device targeted at lithium or some other element and do fusion in the solid state material.
Yes, so the question is, we've got a lot of particle accelerators out there that we're able to produce some very high energy, and we've got one at Oak Ridge National Laboratory, the spallation neutron source. And could we create a beam of particles that would produce the conditions for fusion? And there are people who are working on that concept. And again, I'm the engineer, I'm the box builder, so I'm not so much the person to answer the question as to how feasible it would be to produce an energy source. My initial thought is it might be a challenge to get the kind of fluences, the amount of particles that you need over the length of time. And you're still left with, if you've got a deuterium and tritium beam, you've still got to do something about all the byproducts. And how you confine them. But I'm sure there are both positives and negatives to those ideas. I've seen presentations on that, and there's, in terms of isotope generation, there's a lot of science going on currently to developing these kinds of beam lines. So, sorry I can't give a complete answer to that. Again, I'd be happy to pass on email addresses or phone numbers of people who could answer that question better. Yes?
So how efficient are these things at actually burning the fuel you inject them with? Because I know that in fission reactors, they only burn a small portion of the fission material.
Right. So the question is, how efficient are they in actually burning the fuel? And of course, we've got to do it a few more times, I think, before we'll completely know the answer to that. The advantage of having a circulating plasma like this is you spit it in, and ideally it may circulate till it burns up. Now, that's not completely true, and one of the problems in the material that's going to be facing the plasma is you can end up having tritium come out of the plasma and get into your material. And they talk about the hydrogen, deuterium, tritium permeation issues. So I think in terms of the first circulation, it's something on the order of just a few percent initially that are burned up. But it's very different from, as said, in fission, it's very inefficient. But again, in fission, you've got a large rod that you put in place, and then it stays there for a long time. In fusion, we're going to be dumping a few grams of deuterium and tritium through pellets, through gas, periodically. So it's a very different method of fueling than what you have in a fission reactor. Yes?
Can you speak more about the significance of the stellarator?
The stellarator. Stellarator was okay, let me, I could stay here all day and talk about stellarators. A stellarator is an alternative concept to the Tokamak. I didn't talk about one of the biggest problems of the Tokamak, which is in order to produce a stable plasma, you can imagine a donut. You've got a constant field in that donut region, but the inside of the donut is smaller than the outside. So in a sense, you have a higher field density, and it ends up driving the ions into the inner wall. So in order to make a stable plasma, you have to have the ions rotating around the donut, processing around the donut as they move around. In order to do that, they put a large current inside the plasma that ends up producing that kind of field that causes the ions to rotate. The problem is that current it's very high energy. In ITER, it'll be about 15 mega amps of current in order to produce a stable plasma. Well, if there's some interruption in the plasma, a disruption they call it, then the plasma goes away. 15 mega amps of current. I know most of us are mechanical engineers in here, right? I'm a mechanical engineer. That electrical stuff always was very esoteric to me. But you remember from your basic electrical engineering, you have current going through a wire. It produces a magnetic field that varies with the square, the radius. So you've got this large current producing a large magnetic field. You've got these magnets producing large magnetic fields. And electromagnetic forces are generated proportional to dB dt, the change in field with time. Well, if you have this large current that goes away in a couple milliseconds, you got a very small t and a very large b. So dB dt becomes very large. You have large electromagnetic forces, and you've got a big problem. So that is a difficulty with tokamaks. And every tokamak that has ever been built has had disruptions. And they say, like in GA, in General Atomics, the D3D experiment, that they can feel it. When a disruption happens, they can feel a little tremor in the building. And ITER is many times larger and has much larger fields, much larger plasma currents. So what do we do about this? Well, we've got plans to try and mitigate the disruption, to soak up the energy before it destroys the reactor. There are plans to control the plasma in a way that make disruptions less likely. Another thing is to build a reactor that doesn't require this large plasma current. And the stellarator is one idea. The idea of the stellarator was developed in the 50s by Lyman Spitzer at Princeton Plasma Physics Lab. The largest stellarator ever to be built has just been completed in Greifswald, East Germany. And I've just got to show a picture of it because it's so crazy. The idea is, in order to get the rotation in the plasma, you do it by, instead of putting a big current in the plasma, by creating crazy shaped magnets that generate rotation just by the nature of the magnets. So this is the upper left hand is a CAD model of Wendelstein 7X, W7X, which is this stellarator, and the modular coils are shown there. These crazy shaped, again, superconducting 4-degree liquid helium magnets. What's the size of this? It's maybe, let's see, major radius is about 6 meters. So we'll say from one end in the upper picture to the other is maybe about 30 feet across. So it's a lot smaller than ITER, but it'll be the largest operating stellarator. They're ready to start operation, but the regulatory agencies in Germany need to give their final approval. So the stellarator is a lot more difficult to engineer to build magnets like this, but it's much more stable from a plasma physics standpoint. And it's a competing, there's some, particularly the folks who have worked on this, who say maybe the demonstration reactor should be a stellarator rather than a tokamak. We'll see. It's kind of being held in reserve, I think, if ITER, if it's shown that the tokamak concept, if this disruption problem can't be solved, then maybe the stellarator will be the reactor of the future. Good question. Impressed that you would even be able to ask that question. Yes?
Design News had an article pointing out that there's some very wealthy venture capitalists that are pouring money into various things that may have been tried 20, 30 years ago. Is
Yep.
that a surprising development, and do some of those other alternatives, previously tested things, have potential?
Right. So the question is, venture capitalists are pouring money into other concepts, and there are about a dozen other, not cold fusion, there are about a dozen other reputable, possible concepts, and some pretty big names are pouring money into them. There's General Fusion in Canada, which is a magnetized target fusion. There's the Polywell reactor that the Naval Research Lab is working on. What's the other? Well, the Skunk Works. Anyway, it's getting late enough that I'm having my senior moments. Is this surprising? No, because the payoff is so great. And when Skunk Works came out with the news that they're going to have on the back of a semi-truck a 50 megawatt reactor within 10 years, my first thought was, oh no, I'll be out of a job. And then my second thought was, no, if this works, anyone who knows anything about fusion is immediately going to be scooped up to work on producing these things willy-nilly. So if any of these things work, that would be fantastic. I think the people who have been working on this for decades, who I discussed this with, are skeptical. You've got the same problems, some of the same problems with any of these concepts. That what are you going to do with these high heat fluxes? What are you going to do with all the helium and the neutrons? and there are concepts that get rid of some of the problems you have with the magnetic fusion or with the tokamak, but they always produce other problems. So, yes.
We need to work on all these concepts. And the reason we need to work on them, when I was in graduate school 45 years ago, I was told by smart people from Oak Ridge National Laboratory that nuclear power is going to make electricity so cheap that we won't meter it. We won't have to meter it. I was over at the power board yesterday paying my electric bill, and there were folks in there that couldn't pay their electric bill. So if we can figure out a way to make electricity with this huge source of energy, we need to do that. We need to make electricity and make it cheap, because we got people in the country that can't pay their bills.
Yeah, well, and in this country, that's a challenge. Of course, internationally, it's, China, India, you have that problem. I mean, you have large segments of the population that don't even have electricity. And so, yes, it's an international problem. And I'd agree. Now, I hope I've also given the clear impression that I'm not a wide-eyed idealist in saying this is going to be cheap and easy energy anytime in my lifetime, frankly. It may put watts in the grid in my lifetime. It's not going to be economically feasible unless there are some major unforeseen technological leaps. But I've got to think about my children and their children, and that's, working in fusion, I feel like I'm working not for me, not for the, there are lots of cool things. I mean, what's not cool about 150 million degree plasma? Okay, but really, in the grand plan, I don't like working on things just because they're cool. I've always said, every job that I've had, I've said, I want to make the world better. Not going to probably make the world better in 10 years, maybe not 20, but in 70 years, this may be something that has totally changed the world. And there are a few things that can change the world quite as much as an energy technology like this.
Let's change the world.
All right, well, I appreciate your patience, and I'm happy to answer any other questions one-on-one or in small group here afterwards.